Hi everybody. Today we're going to continue on with the ideas of momentum and conservation of momentum as they apply to something called a collision. Now if you remember, one of the principles of conservation of momentum was the idea of recoil, where two objects start together and separate, one going one way causing the other to recoil in the other direction. Well, collision is sort of the opposite of that. Here now we have two or more objects apart that now come together and exert some sort of force on each other. Now, one of the most important things to remember is that your total momentum is always conserved in every collision. No matter what type of collision, no matter what happens, the total momentum of the system remains constant. However, your total energy is not always conserved. And by that, I mean that there is going to be, in many collisions, some sort of energy loss into the forms of heat, sound, and light. Now, generally, it's a loss of kinetic energy that we're looking at. Because when we're going to look at our collisions, we'll look at sort of the moment right before and the moment right after. So usually there's some sort of kinetic energy that's involved. There are three types of collisions, three categories of collisions. The first is called an elastic collision. And an elastic collision is one that actually is able to conserve both momentum and energy. In other words, not only is total momentum conserved, but there is no energy loss to other forms of heat, light, sound, things like that. So this would give what's called a perfect rebound, simply because there is no energy lost. Now in reality though, it's not really possible because literally all collisions probably produce some sort of sound, some sort of heat effect, things like that. It's believed down at the atomic level, when atomic particles collide, they produce nearly elastic collisions. But in general, it's not entirely possible. But we're going to pretend it kind of is. Good enough. So let's look at a couple of examples. We're going to look at three different scenarios taking an elastic collision where one object will be in motion and the other object will be at rest initially. So in our first one, we have a very large object moving along and it's going to hit a much smaller object that is stationary at rest. And what would the results be? If we consider that large object in motion, it has a lot of momentum. It also has a lot of energy as it moves along. Now, no matter what, when it hits the smaller mass, that smaller mass has to be sent forward at some sort of final velocity. Okay, that's pretty obvious. But the larger one, because it has so much momentum, is able to continue through the collision. However, it needs to have lost some of its initial velocity. In other words, its final velocity is less than what its initial velocity is. And that's because it's going to transfer some of its energy over to that smaller mass. Now let's see if that works physically. Okay, so here we have mass 1, very large, mass 2 kilograms, and it's going to move along at about 4 meters per second, giving it about 8 kilogram meters per second or 8 newton seconds of momentum, and a kinetic energy of about 16 joules. Our smaller mass is going to be sitting here at rest. So let's go. So, a couple things that happen. First of all, that second smaller mass does take off. Okay? Notice with a very high speed, about 6.4 meters per second. And the larger mass, which was traveling initially at 4 meters per second, has slowed down, yet it continued on through the collision. Now, a very important thing, notice the total energy of the system still remains at 16 joules. The 16 joules is not just mass 1, it's the total energy of the two added together. So the total energy was 16 before and is 16 after. Notice also that the total momentum still adds up if I add 4.8 and 3.2 to 8 newton seconds of total momentum. So both momentum and energy are conserved. In our second scenario, we have a smaller mass moving along that's going to hit a much larger mass that is at rest. Now again, because that larger mass was at rest, it's going to get knocked forward with some sort of final velocity. But the smaller one, because they exert equal and opposite forces, because it's a smaller mass, it experiences a much larger acceleration due to the same forces. And because it experiences such a large force and acceleration that's going to act to the left, it's actually going to rebound off and head back the other way. But again, conserving total momentum and total energy. Now again, let's see this in a simulation. Okay, so now we have our smaller mass that has a total momentum of only 2 Newton seconds and a larger mass sitting at rest, smaller one going on at 4 meters per second. Now notice the total energy of the system is about 4 joules. Okay, so this time, upon impact, the larger mass still headed forward, but the smaller one rebounded the other way, heading back in the negative direction. But the total energy of the system still remains 4 joules because total energy is conserved in an elastic collision. And again, if we add the two momentums, now remember, one of them is negative now, so 3.2 plus negative 1.2 gives me 2 Newton seconds of total momentum. So total momentum is still conserved. Our final example here is probably one of the most interesting ones. Here I have two objects of equal mass. One is in motion and one is completely at rest. They'll go along and hit each other. Now, again, that one that was at rest has to take off with some sort of final velocity. But the interesting thing is that final velocity is equal to mass 1's initial velocity. And what that also means is that mass 1 comes to a complete stop. In other words, because they were equal mass, they were able to completely exchange momentum, velocity, and kinetic energy. Okay, complete exchange. And you may have seen this if you've ever seen Newton's cradle, the little balls that bounce back and forth as they hit each other. Because they are equal mass, they're able to always transmit that energy back and forth. Now, let's see if the simulation will verify that. So here we have two objects, both equal mass, both 2 kilograms. One is at rest, and one is going to be moving at 4 meters per second. Total momentum, 8 Newton seconds. Total energy, 16 joules. Now you'll notice that mass 1 came to a complete stop, no momentum, and all the momentum of 8 Newton seconds is transferred to mass 2. Total energy still remains at 16 joules. Okay? Now, what can kind of be even more fascinating is mass 2 didn't even have to be at rest. For example, let's say that mass 1 is going to go along at 4 and mass 2 is going to come straight at it at negative 2. Now watch what happens here. Notice that mass 1 now has a velocity of negative 2 and mass 2 now has a velocity of 4. They perfectly exchange velocities. They also perfectly exchange their momentums. Okay? So, the important idea out of this. A head-on elastic collision between any two objects of equal mass will always perfectly exchange these three things: velocity, momentum, and kinetic energy. But again, that's only head-on elastic between two equal mass objects. Second type of collision is called an inelastic collision. Now this is probably the most common type of collision. Momentum is conserved, but there is some energy loss. Again, these things like heat, sound, light, other forms of energy. So to approach this mathematically, we're going to use conservation of momentum because that is the one thing we can guarantee is conserved, that momentum is conserved. Let's look at an example. Okay, so again, I'm going to have two objects that are going to sort of head for each other, hit. And the first one, traveling along at 4 meters per second. The second one is going to be coming head-on against it at 5 meters per second. Now we got to be careful because it's going the other way, so technically that's negative 5 meters per second. They're going to hit, and let's say that the first one continues to move forward at 2 meters per second. And the question is, what is the final velocity of this second one? Okay, so whether it's an elastic collision or an inelastic collision, we have to conserve momentum. So that's that big long equation. m1v1o plus m2v2o equals m1v1f plus m2v2f. Now again, that equal sign, that point of interaction, everything on the left is the moment before the collision, everything on the right is the moment after the collision. But we know all our values. M1 is 10 with initial velocity of 4. m2 is 2 with initial velocity of -5. m1 still remains 10 but has a final velocity of +2. And m2 has a mass of 2 and then some unknown final velocity. Okay, that's 40. It's -10. That's 20. This is 30. Subtract 20. And we end up with a final velocity of +5 meters per second. And now that makes sense in a couple of ways. One, the first one had a much larger momentum, so it was able to sort of carry through the collision and drive the other one back the other way. So where it was going -5 at the beginning, it's knocked back the other way, so it has a positive velocity. And again, this has a lot to do with the fact that the forces they apply are equal and opposite. Okay, but if the forces are equal and opposite, okay, one of them has a very large mass, so it undergoes a very small acceleration. In other words, it goes from 4 down to 2, very small change in velocity. But the other side has a very small mass, so it must undergo a large acceleration. It went from -5 down to 0 up to +5, okay, complete change in direction. So action-reaction still seems to apply pretty well here. Our third type of collision is called a perfectly inelastic collision. Now, like all collisions, they conserve momentum. But the one thing that signifies a perfectly inelastic collision is that the objects remain stuck together after the collision. So the one thing that will identify it is that they remain stuck together. So momentum is still conserved, but here we're going to get the most energy loss of any type of collision, and that's due to that sticking together. Now, because they stick together after the collision, they have to have the same final velocity because they are stuck together. So, we're going to apply a sort of different version of conservation of momentum, a little modified version. And in here, we start off with the same part on the left-hand side, m1v10 plus m2v20. But now we're combining the two masses on the right side because they're stuck together at a single final velocity. So it's still conservation of momentum, we just kind of tweak the equation a little bit. Let's look at that real quick in terms of the simulation. Okay, so in this example, we have two objects that are going to head towards each other. Okay? One with a momentum of 16, the other with a momentum of -4 Newton seconds. Total energy of the system is going to be 36 joules. Now I've turned the elasticity down to 0, so in other words, perfectly inelastic. So let's watch what happens. Okay, so a couple things happen. One, they are completely stuck together. Okay? Now, the total momentum of the system, though, still remains 12 Newton seconds, much like we added them before. But now we've had a large loss of energy. Okay, went from 36 joules down to 12 joules. Okay? And as you can see, they were clearly stuck together. So let's look at a mathematical example. Say we've got a 2,000 kilogram truck heading down the road at, let's say, 10 meters per second. And it's going to rear end a 500 kilogram car that's sort of slowly going around at 5 meters per second. And they're going to hit and stick together and want to know what their final velocity is going to be. Well, we're going to use our modified, perfectly inelastic version of conservation of momentum, where they're stuck together. Now they're both traveling in the same direction. Okay, it's a rear-end collision. So you got the truck headed at 10. You got the car headed at 5. They are going to become stuck together, moving at some sort of final velocity. Okay, so this is 20,000. This is 2,500. Let's add together is 2,500. Yeah. This is 22,500. Divide both sides by 2,500. And that gives you a final velocity of 9 meters per second. Now, it's kind of interesting. Now, the truck naturally slowed down because it ran into something, but the car actually increased its velocity, and that's due to the momentum impact of such a large vehicle. But what if we reverse directions? What if we have the same truck, but now the car was headed at it? Okay, now they had both better slow down some in this case because they're now making a head-on collision. Okay, perfectly inelastic collision. Now, the number one mistake made in this type of problem, because it's a head-on collision, is the vector mistake. That car is traveling at -5, okay, because it's headed the other way. They're going to become stuck together, some final velocity. And now we have 20,000 here. We have negative 2,500 there. This is 17,500 divided by 2,500, which gives a velocity of positive 7 meters per second. Okay, so not only did the car slow down in the negative, but it was shoved back the other way in the positive direction. And again, because that truck had such an overwhelming momentum. Now, can you take a guess at what situation both vehicles would have come to a complete stop? Well, clearly we need the car to go a little bit faster in order to match its momentum. So it turns out there's only one way to get them to come to complete stop, and that's if they both have not equal mass, not equal velocity, but equal momentum. Again, let's see that in the simulation. Okay, so in this case, I have two objects with very different masses, very different velocities, but they have equal momentum, just in the opposite direction. So this is going to be having a momentum of 8, this one of -8 Newton seconds. They are set to make up a perfectly inelastic collision, so let's see what happens. Okay. As you can see, they hit, they stuck together, and they completely stop. All of the energy is lost, and the total momentum of the system still remains 0. Because if you remember, the total momentum of the system, if we added up before, 8 plus -8 is 0. And so the total momentum at the end is still 0. So all of the energy is lost and everything came to complete stop, but only because they had the same momentum. Let's look at one last example here. In this case, I've got a 4-kilogram crate sitting here at rest on top of a 2-meter high hill. It's going to slide down, we'll say no friction, and it is going to hit and stick, in other words, make a perfectly inelastic collision, with a 6-kilogram object at rest. I want to know how fast they're going after the collision. Okay. Now, if we try to apply conservation of momentum like we should for a perfectly inelastic collision, m1v10 plus m2v20 equals m1 plus m2vf. Now, some people might say, well, both of them have an initial velocity of 0, because clearly that's what I wrote here, right? But that's way, way before the collision. You see, when we deal with conservation of momentum, we have to take this moment right here at the collision, which means that mass 1 was not at rest right before that. So we need that velocity. Well, how are we going to get it? Well, let's go back to our old friend energy. You see, mass 1 at the top of the hill, does it have height? Yes. Does it have motion? No. Springs? No. So its total energy up here is gravitational potential energy. Now, when it reaches the bottom of the hill, right before the collision, does it have height? No, but it does have motion. So its total energy at the bottom of the hill must be kinetic. And if there's no friction, we can say that total energy equals total energy. In other words, we start off with gravitational potential energy. We end with kinetic energy. This is mgh. This is 1/2 mv squared. Now, we're only dealing with mass 1, the one that's moving, so it's the same mass, so we can sort of get rid of it and cancel it. So gravity is 10. We have a height of 2. multiplied by 2. So v squared is 40, or it has a velocity of 6.32 meters per second right before impact. Now, that becomes its initial velocity right before the collision, and that's the value we can use. So now the 4 kilogram one going at 6.32. The second mass was at rest before the collision. They hit and stick. This is 25.28. This is 10. And so together they have a final velocity of 2.53 meters per second. So we can combine energy and a collision together. Okay, so that's basically the idea of conservation of momentum and collisions. Again, there are 3 types of collisions. They all conserve momentum, but they don't always conserve energy. The elastic collision, they hit and bounce off and conserve both momentum and energy. The inelastic collision, in which they hit and bounce off, but only conserve momentum and do not conserve energy. Energy is lost to the forms of heat, light, sound, things like that. And then the perfectly inelastic collision, in which they hit and stick together. Here you get a large amount of energy loss due to that type of collision. Okay, see you next time.